Hello, in this tutorial we will cover the animation and interaction of your scene. First we will have a look at very basic generic animations. After that we can explain methods and events and how exactly they work before jumping to our interaction nodes and keyframe animations. We will start looking at the mover node. It can be found in the animation category of the toolbox. We already used it in another tutorial to animate the rotation of a geometry. But now let us take a closer look at it. Generally, the mover node creates a value based on its inputs and the current time. By default, it linearly swings between the defined minimum and maximum, repeating every second. In the range category, you can change the minimum and maximum, as well as the swing flag. When turned off, it will just start over from the minimum once reaching the maximum. Also, you can define the used function. Besides the linear animation, you can animate in a sine or cosine curve, making the repetition a lot-knit method, without using the values in between. Lastly, you can create random numbers in the defined range, using the duration as the frequency. In the speed with the same settings, generate the same values. Relative uses a mover-specific clock, and you can create asynchronously running movers. One shot will only start once the nudge function has been triggered, and only runs to the end a single time. Infinite will also start on nudge, but will repeat infinitely from then on. You can use this node to create very simple animations like an infinite rotation around an axis, a swing along an axis, or a one-time reaction to a specific input of the end user, by using the one-shot mode and the nudge method. In order to react to an input, we will need to have a look at the events and methods of Ventus first. Basically, methods are commands to a node to start a specific routine and thus are always inputs. Like in the mover node, when we trigger the nudge method, we will tell it to start the routine that generates the values from minimum to maximum, either once or infinitely often. Events, on the other hand, are outputs of a node and will be fired when something specific happens inside the node. For example, the mover node will fire the onRepeat event once it starts over its generation of values. All methods can be bound to all events of other nodes, like you can bind all other types of properties. In contrast to other properties, you can bind methods to any number of events. Different nodes have different methods and events, and like properties, you have to know what they do exactly in order to use them. Now let us jump to the interaction nodes and see how to build a cube that rotates when we click or touch it. There are several different interaction nodes that all can be found in the interaction category of the toolbox. The easiest one is the touch button and can be used for our purpose. Let us place it in front of a geometry in the hierarchy to see what it does. We can ignore most of the input properties, since they do nothing much on the touch button, but more often on the other interaction nodes. The only interesting inputs are the ones in the control category. The enabled flag tells the node whether or not to fire its events, and the intersection type defines whether to test the touch or click against the bounding box of the geometry, or rather the mesh itself, to be more accurate but consuming more performance. Again, this node will be applied to all the nodes in its subtree. So when listening to touch events, it will use all geometries placed behind it for that. When we hover over the geometry behind the touch button in our renderer window, you can see that the touch button already fires events and changes its output properties. These are the touch enter and touch leave events that tell whether a touch input has just entered the tracked geometry or left it. Touch inside tells whether the touch is currently inside the geometry. When we click shortly with the mouse on the geometry, one event will be fired, the single tap event. It is fired at the end of a touch or click when it was not longer than a specified duration that can be defined in the project properties. While the button was pressed, the touch pressed flag was turned on. Tap and hold fires once the touch duration exceeds a certain limit, again definable in the project properties. We can use this to start the rotation of the cube. Just create an axis in front of the cube and a mover in the content editor. The mover has to have the mode set to one shot and generate values between 0 and 360. Now we can bind the output property of the mover to any rotation property of the axis. Lastly, we only need to bind the nudge property to the single tap event of the touch button. Now whenever the touch button registers a single tap, the event will be fired, which triggers the nudge method, which will start the generation of the values by the mover node, which will then be used for the rotation properties of our cube. Of course, there are also other more capable interaction nodes. While the touch button only listens to whether something was pressed, the other nodes have the ability to additionally transform the geometries behind it. Those nodes work as if they were an axis, with the only difference that the user can adjust the parameters through touch or mouse input. Touch translation enables a 2D movement. Touch orbit lets the user rotate the geometries on all axes with simple touches, and scale them by pinching. The touch rotation lets them rotate two-dimensionally. And touch transformation is a hybrid of the translation and rotation nodes and additionally allows scaling. All these nodes can define limits for the transformations and return the current offset in all types of transformation. This way you can, for example, build sliders by limiting the touch translation completely on one axis and use the output of the other axis as a reference for the wanted property. These nodes have a physics simulation that is able to keep the inertia of the touch movement to keep up the translation for some time after the touch has ended. This behavior can be edited with a button on the bottom of the properties window. The inertia simulation category defines this behavior. Velocity threshold shows the minimum speed when the touch was released to initiate the simulation. Deceleration defines how much the speed decreases every tick. Limit elasticity defines the bounciness on the limits of the transformation. Additionally to the inertia, the nodes can have tick markers which they will be attracted to. Tick spacing defines the space between these markers. Attraction threshold changes the maximum speed to start the attraction, and attraction speed affects how fast the geometry will be in order to reach the marker. This behavior can be switched on and off with the behavior apply property. If the motion flag is turned off, the node will still generate the output values but does not affect the transformation of the geometries. This way you can handle the motion yourself. Lastly, you can reset the transformation with the reset category. For each transformation component, you can put in a value the node should reset to. If the duration is anything else than 0, the reset will be animated with the help of the defined interpolation. You can tell the node to trigger the reset method on load, and you can turn on two rules for the reset. You can tell it to break the reset by touching the geometry during the interpolation, and you can break the current touch transformation when the reset method was triggered. So much for the touch transformations. Let us take a quick look at the rest of the interaction nodes. The touch paint node allows the user to paint on the screen or a geometry through touch or mouse input. You can define whether or not and when to fade out the drawn line. You can change the brush size and color, and also add a texture to be used as a brush. And you can switch between drawing and erasing. The touch pattern node tracks patterns that are drawn either on the screen or on the children geometries. Enabled patterns are circles and swipes additionally to those of the touch button. Touch ripples track the touches on the screen and creates outputs whose positions are at the locations of the current touches. This way you can create effects for the touches of your user. The touch marker can be used with devices that are able to recognize markers and returns their position, angle, and whether or not they are found on the input device. Lastly, the web browser is a fully functional browser capable of touch and keyboard input and can be used to either browse the internet or show HTML pages bound to the HTML property. This is all for now about Interaction in Ventus. For the last part of this tutorial, let us take a look at how to create more flexible animations with the Ventus keyframe animation nodes, and how to drive them with interaction or otherwise generated events. In order to work with animations, we now need to jump to the Animate view if you did not already do so. In the animation editor, you can already see the main animation of our scene. Each scene has one of these, and they are accessible throughout the whole scene, no matter in which layer you are. You can always animate any property with it. At times you need more than one keyframe animation, for example in order to animate several objects independently from each other. If that is the case, you can use a keyframe animation node instead of the scene's main animation. This node is placed like any other content node and can be found in the animation category of the toolbox. It works exactly the same as the main animation, with the difference that you can only bind properties that are on the same scene level to the animation. For now, let us work with the main animation and start binding and animating properties. To animate elements in your scene, you need to bind the according property to an animation channel of the keyframe animation. This can be done in several ways with the main animation. You can drag and drop the property name anywhere in the animation editor. This will create a new animation channel that is automatically named after respective node, category, and property. Instead of dragging and dropping, you can also hold Ctrl while clicking the property name to achieve the same result. When you want to use an already existing animation channel to animate the property, you can drag and drop that property onto the according channel. Channels can be deleted by selecting them in the animation editor and hitting the delete key. Instead, you may also open the context menu by holding the right mouse button down a short while. You can also duplicate or rename the channel. You can jump to the bound node or delete the binding to the property by hitting the X next to the entry. Lastly, you can also create subfolders or animation channels in this dropdown without having to know which property will be bound to the channel. When deleting a node that has the last binding to an animation channel, the channel will be deleted as well to keep the animation as clean as possible. The keyframe animation editor has different views, each for another purpose. You can switch through them up here. The time view allows you to adjust the timing of your keyframes. The diagram view gives you the opportunity to change the exact curves of the channels, for example by providing handles for each keyframe. The logic view is there to build interactive nonlinear state logics. Here you can define when to drive which part of the whole keyframe animation. This will be discussed later. The last view, the data view, is important when using Ventus template engine and therefore will be omitted in this tutorial. In order to add keyframes, we can jump to the time view again. Select an animation channel for which you want to add a keyframe. Move the slider to the according point in time and hit this button up here or the insert key on your keyboard. To change the value of a keyframe, move the slider up in it and either change the current value or this value on top of the animation editor. You can change the position of the keyframe by dragging it along the timeline or change the position value up here. To delete a keyframe, you can select it and hit the delete key on your keyboard. Instead of adding and animating the channels manually, you can also use the teach-in mechanism of Ventus. Turn the teach-in on by clicking this button or use the add key of your numpad. Now Ventus saves the current state of the scene and listens to any change of all properties. When done, hit the key again and Ventus creates all necessary animation channels and keyframes to change these properties during the animation. The distance between the keyframes will be defined by the number next to the buttons. If you move the slider in between teach-in intervals, the keyframes will instead be inserted at the position of the slider. Using this, you can create complex animations very fast and do not have to think of the structure of your animation before. Let us move on to the diagram view. Here you have all the functionality of the time view, but in order to keep the view simple and organized, only those channels are shown as curves that are currently selected. You can edit all handles of all keyframes of their channels by simply dragging them around. Additionally, you can define how the handles should be limited. You can lock them completely, only lock the direction and not the speed, mirror them, or handle them completely independently from each other. Also, you can change the interpolation method of your curves from the selected keyframe to the next one. Spline is used to control the curve with the handles. Linear uses a simple linear interpolation. Jump will jump at the end of the curve. Elastic will create an oscillating effect around the new keyframe, and bounce will create a bouncing effect. This is basically it about the diagram view of the keyframe. Next, let us discuss the logic view, showing you the current state logic of your keyframe animation. Ventus is able to animate your scene according to the interactive inputs during the runtime, and thus creating non-linear flows of your animation. This can come in handy, for example, in order to create a turntable. There are different positions of the table that are interesting for the viewer, and he should be able to move from one of these positions to any other position at any time. To achieve this, you can use the state logic. One state of the keyframe animation defines one specific state the scene will be in. For a turntable, this would be one of the positions of the table. You can move from one state to another by using transitions. These define an animation that has to be driven to get the scene from one state to another. So a transition would be the rotation to another state of our turntable. States can be created by double-clicking somewhere in the logic view or using this button up here. Create a second state and a transition between them by right-clicking and dragging from the S1 to S2. By double-clicking on that transition, you can jump to the time or diagram view of it, whatever was open last. You can define the keyframes between your two states. Each state itself has a keyframe on each of the channels to define the exact state the scene should be in whenever it is at the specific state of the keyframe animation. Let us keep this animation simple by only using just one more state with only the rotation of the geometry from 0 to 120 to 240 degrees and back. Now let us use the 3 buttons in the other layer to output 3 single tab events. We now want to control the animation with these 3 events. One button lets us go to the first state, the other one to the second, and the last one to the third. In order to do that, we need to bind the according methods of our keyframe animation to the button's events. The methods can be found on the side of the logic view of the animation editor. Here you can see that we have the begin, next, previous, present, and end method. You can see that the icons of the next and previous methods are also placed on the ends of the transitions. These represent the rules that the state logic follows. So in this case, whenever the keyframe animation is in state S1 and the next method is triggered, it will drive the transition between S1 and S2 to reach S2 in the end. When now the previous method is triggered, we drive back to state S1. Right now we only have 2 methods to control our animation, which may be fine in some cases, but we want to, for example, jump to S3 whenever we hit the 3rd button in the scene, no matter in which state the animation currently is. As it is right now, we would need to trigger the previous method when in S1 and the next method when in S2. This will be very hard to implement with only those 2 methods. So let us add 3 custom methods in order to use them for the specific logic. Click the Edit Custom Model button. In this window you can add as many methods as you want to the default ones. Let us create one for each state. Now we only need to bind these methods to the according ends of our transitions. Just drag and drop those onto the old methods. Now you can bind the methods of the animation to the right outputs of our 3 buttons, and the state logic is readily built. You can now animate from each state to each other state at any time. In order to completely delete a method, you can right-click it and choose Delete, and to delete the whole transition, you can select it and hit the Delete key. The other 3 methods of our default set of methods are jump methods. Whenever begin is hit, the state logic will immediately jump to the begin state of our logic, which is in our case S1, the green state. The same goes for the present and end methods. In order to make a state a begin, present or end state, right-click them and choose the respective entry. Your custom methods can as well be used as jump methods by placing them not on the ends of the transitions, but rather on the states themselves. Now whenever the method is hit, the animation will directly jump to that state. This now closes the tutorial about interaction and animation. Use these new insights to build a lot more interesting scenes in your projects. The next time we will talk about how to use external data like Excel or XML files and how to create very simple logics to use or visualize them in your scene.